In this particular chapter, we will have a look into, or in this particular lecture, we will have a look into the skewing effects on the pulse latch, which was left. We had earlier seen the skewing effect on the flip-flops as well as on the transparent latches. So let's take this pulse latch design. Let me also pick my pointer here. And in this particular, timing diagram, I've clearly shown the pulse latch. The circuit diagram of this pulse latch remains the same. So we will use the pulse latch here, PL1, which will go to the combinatorial circuit number 1, and then it will go to the pulse latch number 2. And as we know that the clock here will be there, and then the same clock will be going into the pulse latch 2. And for the finding the maximum delay constraints or establishing the TPD, the maximum TPD that needs to be characterized for the combinatorial circuit number 1, we always see the worst case condition. And then the worst case condition is the PL1 receives the clock which is kind of delayed, and the PL2 receives the clock which is kind of early. Right, because we don't know really the placement of the latches in the chip, and that's where the skewing effect comes into the picture. And then the skewed clock characteristics, if it is available, we will consider the worst case condition. Right, so here in the clock designs, I've drawn the skewed effect of the clock. So here the T skew is kind of characterized and then made available to us. So if I consider this the T skewing parameter with respect to the clock, we say that this particular clock, the black lines, not the dotted ones, the black lines is the clock which is arriving early, and the dotted lines is the one which I'm saying that the clock is arriving late. And as as per our condition, that the worst case condition, the first pulse latch is going to receive the arriving late clock, and then the second pulse latch is going to get the early clock. Right. So with that in mind, let's then try to understand the data flow of this particular the subsystem design. So if this D1 is the input to this latch 1, so this is the latch 1, the D1 is the input. So if it is made available before this skewed clock, then I will get the Q1 signal after the clock to Q propagation delay. Right, and that goes to the combinatorial circuit number 1, which will give the output after the propagation delay of the combinatorial circuits. And then this particular delayed or this particular output of the combinatorial circuit should be made available at least before the T setup time of the clock that is going to the the pulse latch number 2. And that is, that the clock for the pulse latch number 2 is nothing but the clock arriving early. So I've drawn the T setup time with respect to this black line clock signal and not with respect to the dotted lines, because this is the clock that has been arriving early. And here the TPCQ I have drawn with respect to the dotted lines because the pulse latch is actually receiving the clock that is arriving late. Right, so if this is the particular timing diagram and its parameters associated with it, what should be the clock time period, or what should be its propagation delay of the combinatorial circuit that we need to design? So, so if I consider this particular clock time period from black line to the black line or dotted lines to the dotted lines, that will be TC. And if I notice this TC minus TCQ will give me this particular dotted lines to this particular point. So TC minus TCQ will give me, starting from here, point A, I'll write it, and then to here, point B. Right. And if I have A and B, so I can do A, B plus the TPW will give me this TC point. Right, so now I have this particular whole duration where I can actually use the TPCQ, TPD1, and then the T setup. Right, so on right hand side I have TPCQ, TPD1, and T setup, and on the left hand side I can say that the points A to C. Right, the duration from the A to C, which is nothing but TC minus TCQ plus TPW. Right, and what we really want is this the A to C points, the duration which is defined by TC minus T skew plus TPW should be greater than or equal to this the parameters TPCQ plus TPD1 plus T setup. Right, so this particular A to C point should be greater than or equal to the other three parameters. right? So in that sense, what we have is the TPD value is now should be the maximum TPD value turns out to be TC minus TCQ plus TPW minus of TPCQ minus of T setup, right? So notice that if the T skewing was not there, right, the TPD value would turn to be higher. If it is there, the TPD value turns out to be lesser. So the maximum delay constraints has been reduced further, right? So this is the overall expression for the clock time period for the pulse latch with the pulse which has been generated by the clock, right? And then having the clock as having the skewing characteristics. Right, so the maximum delay constraints for for the TPW, the pulse width that is being given to the pulse latch is actually very small, then we will have this particular expression. But if the maximum delay constraints, if we are trying to see for the pulse width to be very large compared to the T setup time, then it behaves like a latch, and we know that the latches, it is actually skew tolerant. In fact, the propagation delay that is for the combinatorial circuits, if we design for the latch, it is kind of skew tolerant, so the TPD value doesn't have an expression where the T skew is involved. And that is what is likely to happen even if we have the pulse width to be very higher, right? If the pulse width is lower, that is when we will have this particular expression, right? So in this particular case, in this particular diagram, I've drawn the pulse width to be low compared to that of the T setup time, and that is kind of seen here. The T pulse width is very small compared to the T setup time. Right, so moving ahead, what should be the minimum delay constraints with the clock skewing? So for the understanding the minimum delay constraints, we will say that the pulse latch 1 will get the clock that is arriving early, and then the pulse latch 2 will get the clock, which is the dotted lines, which is arriving late. So the clock arriving early for the first latch and the clock arriving late for the second latch. And with this TPW also there, the T hold time will be with respect to this dotted line after the TPW, right? And if the first latch is receiving the signal D1 and its output, which will be the contaminated output TCCQ, will start with respect to the first, the rising transition with respect to the pulse signal. So I'll get the TCCQ, followed by, the Q1 will go to the combinatorial circuit number 1, and then the combinatorial circuit number 1 will throw the contaminated output after the TCD time duration. Right, so I will have a TCD time duration, but we need to ensure that, the TCCQ and TCD should surpass this T hold time, so that it will be getting captured in the second clock and not in the first pulse, right? So for the second pulse latch, what we need to do is the output should get captured not in the first pulse, but rather it should be captured in the second pulse. And for doing that, we need to make sure that the TCD value and then the TCCQ should be able to surpass this T hold time. Right. So if I look into the expressions here, the TPW plus T skew plus T hold, and then on the one side we have the TCCQ and then the TCD. So TCCQ and TCD should be greater than these three parameters. So T hold plus TCQ plus TPW, and then on the other side we have TCCQ plus TCD should be greater than or equal to the other three parameters. All right. So what it means is the TCD value turns out to be greater than or equal to T hold plus T skew plus TPW minus TCCQ. Right. Effectively, what we are seeing is the T hold time. If the T skewing is added, if the T skew is characterized in the minimum delay constraints, the TCD value needs to be increased when the T skewing was not there. Right. So effectively, the T hold is going to be increased. So the T hold time effectively increases if I consider T skewing as one of the T hold parameters. Right. With the TPW also, the TCD value will be increased. So if I consider the pulse latch with respect to the flop designs, the flop design doesn't have this, the TPW parameter. And so my TCD that we'll design for the flop designs, and when I compare with the TCD, when we use it for the pulse latch designs, we will not have this TPW parameter. And thereby, for the flop designs, the TCD is much more relaxed, whereas for the for the pulse latch, the TCD parameters is much more constrained because my TCD value has to necessarily be greater, right? And then it goes closer to that of the TPD of the combinatorial circuits. right? So in that sense, we will have much more constraints in the pulse latch designs. So hope this is clear. Moving ahead. So let's see an example here of the T-skew of 50 picoseconds. And we have the flop designs and then the adder mux1, mux2 and mux3. And then we also have another data path here. So there is one data path coming from adder muxes, 3 muxes. This is path 1. Oh, sorry, this is path 1. And then there's another path here, the mux4, mux2, mux3. This is the path 2. Right, the propagation delay and then the contamination delays of this particular blocks, combinatorial circuits blocks, are given here: 590, 60, 80, 70. Contamination delays are also given here: 100 picoseconds, 35, 55 and 45 picoseconds. For the mux4, the propagation delay is 110 and then the contamination delay of 95 picoseconds is given. Right, and the flop is only one flop, but the output of this combinatorial circuits will pass into the flop designs and then keep doing that for every clock cycles. The question here is, what should be the TC minimum that needs to be designed so that to accommodate the T skewing factor of 50 picoseconds. The flops characteristics is also given here: T setup time, TPCQ, TCCQ and T hold time. Right, so the minimum clock time period that needs to be addressed or that needs to be designed is TC should be greater than or equal to, and this is a flop design, so I will use the flop design timing diagram parameters, which will be nothing but the TPCQ value plus the TPD plus the T setup plus the T skew. Remember that, in the timing diagrams, we had seen on one side TC minus of T skew, right? On the other side, we had TPCQ plus TPD plus T setup, and then TC minus T skew should be greater than or equal to these 3 parameters. I've taken the T skew on this particular side. So we will get the clock time period should be greater than or equal to this particular 4 parameters. So the TC minimum is nothing but TPCQ. I can take it from here, which is 50 picoseconds. And then the TPD will be 590 plus 60 plus 80 plus 70. It turns out to be 590 plus 210, which is 800 picoseconds. And the T setup is 65 picoseconds, and then the T skew is 50 picoseconds. So I'll write this. So I'll get, so this 800, all right, this is 800 plus 50, 850 plus 50, 950 plus 65, 965. So the minimum time period, the clock time period that has to consider the clock skewing is also 965 picoseconds. Right, and I've not introduced the path 2 here. The path 2 anyways, the propagation delay will be less, because considering the adder, which is 590 picoseconds, and comparing with this particular path of 110, 80 and 70, this particular path of adder, mux1, mux2 and mux3 will be much more higher. So my TPD value here, if I consider the path 1, will be more higher than that of the TPD for the path 2. All right, so this becomes my critical path, or this becomes the path where the delay is higher. Right, so the other, in the same example, the same designs where we have the path 1 and path 2, how much is the T skew that has been allowed before the hold time failure occurs? So let's say that the clock characteristics are not given to us, and then we are supposed to design it and then say that, what should be the clock skewing, and then let's say that the clocks are available in the standard cell libraries. Based on the skewing parameters, I can actually choose the clock standard cell library. So in that sense, what should be the T skewing characteristics? So if I have this particular subsystem design or the data path system design, we still have 2 paths. One is the adder path number 1. And another path is this one, the muxes going to mux2, mux3. This is path number 2. All right. Right. So, and then we need to find out what is the how much T skew is allowed before the hold time failure occurs. Right. So it's a hold time. So it is basically the minimum of the contamination delays, the minimum of the contamination delay for the path 1, the contamination delay of the path 2, and whichever one is minimum, we should consider that. Right. So if I consider the contamination delays, we definitely know that the adder of 100 picoseconds and 135 picoseconds is actually more than that of 95 picoseconds. So I'll have to consider this part 2 designs for considering the hold time failure. So the TCD value, the TCD value here turns out to be 95 plus 55 plus 45. And if I'm trying to find out the timing diagram and then express my T hold time, we know that for a flop designs, the T skew, the skewed clock is there for the next flop. So we will have the T skew followed by T skew plus T hold, right? And then TCCQ plus TCD should be greater than or equal to T hold plus T skew, right? So in that sense, I will have my T skew here. This TCCQ plus TCD should be greater than or equal to T hold plus T skew according to the timing diagram for the minimum delay constraints. So T skew will have to be less than or equal to TCCQ plus TCD minus T hold. And then this TCD is nothing but 95 plus 55 plus 45 and minus of T hold of 30 picoseconds. Here the TCCQ, I'm considering it to be 0, which is not appropriate, which is not correct, in the sense what we are assuming is in this particular data path system, this MUX4 input to the MUX4 should also be timed. We are considering it is not to be timed at all, and it is it is appearing from the first clock, and then that's why the TCCQ of 0 is taken here. And then this 95 plus 55 plus 45 minus 30 turns out to be 165. So we are saying that T skew should be actually be less than 165. Right, so the T skew from 0 to 165 is kind of allowed, which is kind of inappropriate if we consider this to be 0. So what do we do? So let's say that this MUX4 is also timed. That means that we will also use some kind of a flop here, which will have the same characteristics as that of this. So if I use this TCCQ, I will get this 35 picoseconds. So this 35 picoseconds has to be added here. So it will go to 165 plus 35 picoseconds. So in fact, the T skew that can be allowed is 200 picoseconds, because I have considered this MUX4 input to be a timed one, so which has a 35 picoseconds, right? So my T skew that is allowable is around 200 picoseconds, and what we are assuming here is the MUX4, whatever is the timed one, so that particular flop and then this particular flop are actually having the same characteristics. So now if I know that this is the T skew that could be allowed in this particular circuit design, I can easily say that I can easily choose a clock which is having the skewing from 0 to 200 picoseconds. So not more than 200 picoseconds. If it is more, then we will have a hold time failure. Right, hope this is clear. So this completes the static timing analysis part, and then where we had seen the clock skewing effect for the pulse latch, and also we considered some of the examples for the flop designs, and then what should be the skewing factor, or what is the allowable skewing factor that we can choose for a clock for a particular data path subsystem example, right? So in this particular, the short lecture, I'm just going to introduce you about, the latch designs. Generally in a latch or a sequential designs, we will see the clear signals and then, the set signals or the preset signals. Now, how do we accommodate that clear signals as well as the preset or the set signals in the CMOS latch designs, right? So notice that this particular latch designs, if I consider a CMOS latch, this is nothing but the transmission gate. So this is what we have. So the phi goes here, assuming that this is a positive level latch. And then we have an inverter at the output side to make it insensitive to the noise. And then we have a tri-state inverter to ensure that this particular node is staticized. And then, the staticizing is, we keep the staticizing only during the opaque state. That is when during the phi going low. That's why we are giving a tri-state inverter here with a clock of phi bar and phi here. And another inverter is added here in the Q signal, because if I have this inverter and then this inverter, it can bring back the output noise signal. And that's why we have this particular, the inverter here to ensure that the output noise is not coupled inside the latch. And we used to have this inverter to ensure that the input noise is not coupled into the it's not passed into the latch internals of the latch. right? So this is our latch design. But now if I want to introduce a clear signal, right, if what it means is if the clear is 1, the output should be 0, right? And if it's a synchronous clear signal, so what it really means is only when the clock is high, if the clear is pressed, right, during any time in the clock level being high, then we will get the clock to be 0, output to be 0, right? When the clock is actually low, even if I press the clear signal continuously, right, we will not get any output to be 0. The output will be the previous state output. So that is what it means, the synchronous clear signal for this latch. So one easiest way to do is replace this inverter with that of the NAND gates, right? So an 2-input NAND gate where the one input is the D input signal, the other one is the clear signal, or rather the clear bar signal. So if the clear is 1 here, when the phi is 1, that means in the transparent mode, or when the latch is kind of tend to be operating, when the clock is 1 at a high level, we can, if we say that the clear is 1, the clear bar will be 0. So this will become 0, and then the output of this NAND gate, irrespective of the D input, right? Irrespective of D, whether it is 1 or 0, it will give me 1. So this will throw a 1 here because the transmission gate is going to pass because the phi is equal to 1 here, and then the Q will be 0, right? And that's why this particular circuit design, we can say that it is synchronous clear signal for the latch, for the CMOS latch. All right, so when phi is equal to 1, X will be 1, and then Q will be 0. Right, and if I have the phi to be 0 here, and even if I press the clear to be 1, the clear bar will be 0. Even then, irrespective of the input, I'll get a 1 here, but the phi is actually 0, so this 1 is not passed to the other side of the transmission gate, and that's why we call this design as a synchronous clear signal for the latch. So in the previous slide, we had seen how do we clear the output of the latch design. Here in this particular case, so we are using a preset or a set signal. So the preset or a set signal is likely to give an output of 1 here. So and in this particular circuit design, it is not only the latch but also the preset as well as the clear control signals. Both of them have been accommodated or incorporated. And both of them, are applied for a synchronous set of the latch. So that means that whenever the phi is 1, and if one of the control signals are operating, that is when we will get the Q to be 1 or 0. So if it is set, then we will get the Q to be 1. If it is clear, if it is, the clear is pressed, then the output will be 0. All right. So in this particular case, if let's say that, the set is 1 here, and let's say clear is not at all pressed. So clear as such, clear will be 0. So clear bar will be 1. And irrespective of the D input here, because the set is pressed to 1, I will get an output of 1 here, which will throw an output of 0 here. The 0 is passed during the clock level is high, and so this is going to give an output of 1. So when the set is pressed, when the clock is high, that means the synchronous set signal for the latch, that is when I'll get the output to be 1. Right? When the clock is not 1, or the clock is not high, that means that the clock is low. And if I keep on pressing the set signal, then even though I will get a 1 and a 0 here, it will not be passed to the through the transmission gate. Right? So in that sense, I will not get the output of 1 when the clock is low, right? And then similarly, if I have both the control signals, if if I want to press the clear, I will depress the set signal. So I will not activate the set signal and then press the clear signal. So this clear bar will be 0, and then that 0 is going to make the output of the 2-input NAND gate to be 1. This 1 is going to pass through the transmission gate, and Q will then be 0 instead of 1. So based on the clear or the set signal that is being pressed, we will get the output to be 0 or 1. Right, so that clears this particular part of the slide. Now here I have actually written one particular condition where there could be a contention. Right, although you will not realize that, but let's say that what happens if the set is 1 and the clear is also pressed. So the clear bar is actually instead of 1, it is actually 0. right? In that particular case, if the set is 1, no matter whatever is the D value here, D input value, it will be 1 here. But because the clear is, the 0 here, so that means clear is pressed here, so that means clear bar is 0. So the 2 input NAND gate is going to throw an output of 1 here, right? Because the clear bar is 0. All right. And if that is 1, then this will be 1 when I'm assuming that the clock is high, and then the output Q will be actually be 0. So when both of them are actually pressed, right? So the clear actually takes the precedence. So the clear signal takes the precedence here. If both of them are activated at the same time, or if both of them are pressed at the same time. So the designer, and although these control signals are made available, the designers, when they're controlling the signals, the set and the clear, one should be careful that both of them will not be pressed at the same time. The other way is to give the set more precedences, to swap the positions of the set and then the clear. So this particular NOR gate, if I put it here, and then the NAND gate, if I put it here, the other input of the NAND gate is the D signal, and then this particular, the input is the clear. Then in that case, the set will take the more precedence than that of the clear signal. So hope this is clear. So in this particular slide, what we have seen is the synchronous set and clear signal for the latch that has been accommodated into the latch design. And because it's a synchronous signal, that means that whenever the latch is operating, that is, the latch is in a transparent mode, that is when the clock is high, then only if I press the set and clear signal, we will get the output to be high or low, right, based on what control signal is being pressed, right? Hope this is clear. Moving ahead. Let's take a look at the synchronous set and clear signal for a flip-flop. So in the last slide, we had seen for a latch design. So in this particular case, so if I use the same thing, the set and the clear, right, and then this particular portion is going to give me one particular latch. So this is the first latch, and then the another transmission gate is going to give me the second latch, right? And the first latch is operating in the high level of the clock. The second latch is operating in the low level of the clock. So this particular flip-flop is a negative edge flip-flop. So that's what negative edge flip-flop, triggered flip-flop. And the reason is nothing but if the input is passed through the high level of the clock, and then it has to wait till the negative clock does the transition, or the clock does the negative edge transition, and then goes into the negative level of the clock, or the low level of the clock. That is when the input is passed through the next transmission gate, and then it appears at the output. So during the negative edge of the clock, that is when the input from this particular flip-flop will be passed to the output. And these two particular, the tri-state inverters are placed here. So this particular tri-state inverter and this particular tri-state inverter will ensure that the node X and Y are subsequently staticized, right? It doesn't, it makes sure that those nodes are staticized and not dynamic anymore. And this tri-state inverters are there. They are operating in the opaque mode of this particular latch 1 and opaque mode of this particular latch 2. And notice that this particular tri-state inverter is actually operating in the complement of this clock for the latch 1. And then this particular tri-state inverter is operating in the complement of this clock for the latch 2. Right? So if the latch 2 is operating at 5 bar, that is the low level, this tri-state inverter will operate in the high level of the clock. And if this particular latch is operating in the high level of the clock, this tri-state inverter will operate only in the opaque mode, that is the low level of the clock. Right. So with this particular understanding, we have the set and clear signal here, and we want the synchronous set and clear signal for the flip-flop. Right. So if the clear is 1 here, so if the clear is 1 and let's say the set is disabled. So if the set is disabled means set is made 0, and if the clear is made pressed, so I'll get a clear bar to be 0. So irrespective of the D signal here, I will get a 1 here. And then this 1, if it is a positive level that is being running around, so I will get a 1 here. And then I will get, X will be 1 and then Y will be, so this will be, So yeah, x is equal to 1, and then this will be 1 at this particular, or rather this will be 0, and then y will be 0 in the phi bar. Okay, and then this 0 will be passed into the output 0, right? But notice here that I need to press this clear signal, right? And it has to be pressed for the entire duration of the t setup time and then the hold time, right? If I press the clear signal and then release it, then the D will take the precedence, right? So what I mean is, if I have a clock here, so I'm drawing the clock signal here, we know that the latch number 1 operates here, and then the latch number 2 operates here, and then so on. And this is a negative edged triggered flop, so that is, so I'm drawing the negative edge of the clock. The clear signal, so this is the clock signal, and then let me draw the clear signal also. So the clear signal should be pressed, right, before the t setup time, and it should be retained till the t hold time at least, right? So that, this is the t hold time. So I'm going to write it as the t hold, and then this is as the t setup time. All right. So it has to be pressed for this particular duration of the t setup and t hold, so that the output of here, the output of 1 is passed to the x node as 1, and then after the inverter it is to be 0. And this 0 should be made available as soon as this particular negative edge transition appears, so that that 0 will pass across this particular transmission gate and make the Q to be 0. Right, now the question is, if I actually don't retain it during this setup and hold time, if I actually make this clear signal come down, right? So if I don't maintain it for this t setup time, and if it comes down, then there is a possibility that the clear, when it comes down, right, the D signal, which was, whatever the D input was there, it might take the precedence and then pass. At the output, we will actually get a D output, right? Whatever is the D signal that has been provided to the flop, that might appear. So it might actually get sneaked in. So even if you wanted to have a clear signal, we will not get the clear, we will not get the output to be 0. So that's a possibility. So to avoid that, we ensure that the clear signal should be pressed at least before the t setup time, and should be held high till the t hold time. Right. Similarly, if I want the set signal or the preset signal, then the Q should be 1. In that sense, the clear is disabled, or the clear signal is depressed or made it 0. And if set is 1, I'll get a 1 here, and then that will be followed, and then the Q will be made 1. Right, so that's what I've given. If the clear is made 0 and then set is made 1, I'll get an x to be 0 and then y to be 1, because x to be 0 and then y will be 1, and then from 1 the Q will be 1. Right, and again notice that the set signal should be ensured that it is retained for the t setup and t hold time. Right, one more information here is, if you notice, the latches or the flip-flop designs, we used to have an inverter here instead of the 2 input, the NAND gate. All right, and then our t setup time used to be, if I really want to characterize the t setup time for a particular latch or a flip-flop here, it used to be this particular inverter delay followed by the transmission gate delay and followed by this particular inverter delay. Now, what we have done is this particular NAND gate is being accommodated instead of the inverter to accommodate or incorporate this clear control signal. So my t setup time, or rather the characterizing the t setup time for this particular flip-flop designs or the latch designs, will be, instead of the inverter delay, it will be now be the 2 input NAND delay followed by the transmission gate and followed by the inverter. So that my t setup time will be recharacterized, right, for this particular circuit. And so if I want to have the clear, so this will be the updated t setup time, because my circuit is now slightly updated. So the updated t setup time. So the clear should be pressed for an updated t setup time plus the t hold time, so that I'll get the Q to be 0. And similarly, if this is my circuit design, the set signal should be ensured that it stays high for this part of the delay, plus this part of the delay, plus this part of the delay, and then plus this part of the delay, right? So that determines the t, the set signal should be made high till all this 4 components before the negative edge of the clock, and then plus the T hold time, right? So while we are pressing, while we expect, or while we are trying to do the clear, the output to be clear, the clear should be there before the updated T setup time. Whereas for the set signal, whereas for pressing the set signal, we have to ensure that we have to also accommodate this particular delay as well, apart from the T setup time that is being characterized by this NAND gate delay, transmission gate delay, and inverter delay. So I need to, whenever I'm pressing or whenever I'm expecting the set, the Q to be 1, or presetting the flip-flop designs, ensure that it is slightly, early. So the set signal or the preset signal should be slightly earlier than the T setup time, which I use it for the clearing the signal or providing the D input.